at the beginning of class and go over the quiz, because I think that's a nice chance to discuss ideas and concepts a little more. And you can also check out my solution to the quiz on Blackboard, as well as to the problem set. And let me also just tell you that this afternoon I have a meeting over at University Hall from 2:30 to 4:30. I know that impinges on my office hours. I'm sorry about that. It's out of my control. Okay? But just wanted to give you a heads up in case you were looking for me this afternoon between 2:30 and 4:30. You won't find me. Okay? All right, so let's go over this quiz, talk about the key points. In my opinion, none of these calculations are difficult. That's not the idea of this, to make you go through a lot of crunching mathematics. It is to make sure we understand ideas. So the situation is a gas of dilute atoms, each having mass m, in thermal equilibrium at temperature T. We're going to denote the velocity of an atom by the usual symbol, V arrow. Its three velocity components by Vx, Vy, and Vz. And its speed, which we have to understand means the magnitude of the velocity, with just an italic V. You may assume that each atom has only translational kinetic energy in three spatial dimensions. It's a dilute gas, so they don't interact with each other, so it's just kinetic energy. Take the system to consist of an atom chosen at random and the reservoir to be the rest of the atoms. Then I give you some standard Gaussian integrals in the Gaussian family of integrals, 3 of them specifically, and then away we go. Number 1, think of each velocity vector as a possible state of this system. Write down the Boltzmann factor for the system in terms of the usual symbol beta, 1 over kBt, the mass m, and the velocity components. So we have to know, of course, that the Boltzmann factor is e to the minus beta times the energy corresponding to the state. Often we use the symbol S. That's just a way to denote a state of the system. In general, kind of generically. Here, we're going to denote the state by the velocity. So, if we use the notation for this problem, I would say, well, the state is determined by the velocity components. But the only energy we have here is kinetic energy of an atom moving around inside some container. So we just have to know the standard formula for kinetic energy. 1/2 times mass times the speed squared, where the speed squared means to take the sum of the square of the velocity components. So this would be negative beta m over 2 times Vx squared plus Vy squared plus Vz squared. Okay? And that's our Boltzmann factor. And so we've done question 1. Question 2. We're going to write down an expression for the partition function for this system. We're told we get to use classical physics. And we're going to have I set it up for you. I give you the format of it. It's a triple integral. Okay, so the partition function, which we generally write as the sum over states. So we often write sum over S, but S is just a generic symbol for the states the system can have. But in the classical limit, we're going to write that as an integral. And we have 3 quantities that determine the state, Vx, Vy, and Vz. So we're going to have a triple integral over the values of Vx, Vy, and Vz. So there's an integral over dVx values, and the entire range of dVx values, negative infinity to positive infinity. And then an integral over dVy values, and then an integral over dVz values. And when you convert the sum to an integral, you get factors like 1 over delta v sub x and delta v sub y and delta v sub z. I lumped all those into a constant out front. that you do not have to worry about. Okay? The only thing you have to worry about is what goes in each of these three spaces. What is being integrated with respect to Vx, with respect to Vy, and with respect to Vz? Well, the partition function by definition sum over the states of the Boltzmann factor for each state. So that's why we needed the Boltzmann factor, because that's what gets put down here in the integral. And of course, wonderful property of the exponential functions is that when the argument is a sum of terms, I can write that as a product of separate exponential functions. So I can break this into three exponential functions multiplied together. One that depends on Vx squared, one that depends on Vy squared, one that depends on Vz squared. And then I can put each of these in their appropriate integral. Okay? So here, I'll have e to the minus beta m Vx squared over 2. Just that exponential function for the Vx integral. And then here I'll have e to the minus beta m Vy squared over 2 for the Vy integral. And e to the minus beta Vm Vz squared over 2 for the Vz integral. And I said you don't have to evaluate those integrals, although they can be done, because they're each just a Gaussian integral. But I said don't worry about it, just leave it like that. That's equation 1. So all you do is write those exponentials in the appropriate places. And we've done number 2. Number 3. Well, we're getting ready for the rest of this quiz to calculate thermal average values of different properties of the system, anything we might choose. Okay? So I remind you in question 3 how we stated generically, if I have some quantity Q and I want to calculate its thermal average value, the way we do it generically, sum over states, take the value of the quantity Q for the given state S and multiply it by the probability of state S. Okay? We're again reminded to think of each velocity vector as a possible state. So the sum is really going to be a sum, converted to integral, over Vx, Vy, and Vz. Okay? But for now, all you have to write down for me is the probability part, P. Okay? Write down the expression for the probability in terms of the Boltzmann factor and Z. Here, I want you to note that in the canonical formalism, the probability of a given state is the Boltzmann factor for that state over the partition function. So we are going to denote our states by the velocity vector components. So I want the Boltzmann factor for a given state over the partition function. So I would write that as e to the minus, just use the Boltzmann factor from question 1. Over the partition function, where the partition function is given above in the equation we labeled 1. That's what goes here. And this sum over states is going to be converted again to an integral, but it'll be a triple integral. An integral over Vx, an integral over Vy, and an integral over Vz. And then here is sitting whatever the thing is that we're told to average. So now, number 4. Here's the first thing we're told to average. Okay? So it says that in the classical limit, the sum over the states is going to become integrals, in this case over the velocity components. And we are to find in problem 4 the thermal average value for the x component of the velocity squared. So that if you want to think about what it would mean physically before we do the calculation, it just means at any given time, you poll every single atom, and you say, what's your Vx? Just Vx, please. Don't tell me anything else. Just Vx. What's your Vx? What's your Vx? What's your Vx? Get them all, square them, add them up, divide by n. That's how you would do it conceptually. How do we do it in the canonical formalism? Presumably we'll get what will be equivalent to that. We use this approach right here for finding the average value of any quantity, q. Well, the q here is then Vx squared. Okay? And the sum will be a triple integral. So, and the denominator will be z, the partition function, where we're now going to rewrite it out like we did in step 2. But in the numerator, we're going to have an integral over Vx, and an integral over Vy, and an integral over Vz. Limits are from minus infinity to infinity. Okay? That's the equivalent of that sum. Now, what gets put in each of these spots up here in the numerator? The quantity being averaged times that part of the probability that's in the numerator, which is the Boltzmann factor. But the Boltzmann factor, like we did in equation 1, should be broken up into 3 separate exponentials multiplied together. One that depends on Vx squared, one that depends on Vy squared, one that depends on Vz squared, and then they've got to be put in their correct space here. And remember, the thing that's being averaged is multiplying the Boltzmann factor here in the numerator. The thing that's being averaged is Vx squared. So that's got to be put in the proper place up here in the numerator. Well, since it's Vx, it's a function of Vx, it's got to be in the Vx integral. So what you've got to have here in the Vx integral is Vx squared, since that's what I'm averaging, then also multiplied by the Boltzmann factor that depends on Vx. Now what's left in the numerator? Well, there's the Boltzmann factor that depends on Vy, so that goes in the Vy integral, and there's the Boltzmann factor that depends on Vz, so that goes in the Vz integral. Now that's just the numerator, I'm not done yet, but let's pause and ask another question. What if I had asked you to average Vy squared? What would be different?
Next to the Boltzmann factor, it'd be Vy squared.
There'd be a Vy squared here. What would be here? A 1. Yeah, okay? Right? I can ask you any kind. I can ask you what's the average of Vx times Vy? What's the average of Vx squared times Vy cubed? What's the average of Vz to the 4th? Do you see how you would just put in the appropriate function in the appropriate slot?
For example, for Vx squared and Vy squared, then each integram will have product.
You got to put the symbol in the appropriate integral. So Vy squared has got to go in the Vy integral, right?
So there's just a fewer terms and those that cancel out, basically.
Well, you mean what we're going to do? What's coming out? Yeah, yeah. Okay? Because we still have the denominator to worry about, right? In the averaging process, it involves the probability of a given state, but that has a factor of the partition function in the denominator. So I'm going to now put the partition function in the denominator, and all I'm going to do is rewrite equation 1. Or, by the way, I have another factor of c out front, because I have another triple integral. Okay? So I just put in equation 1 from above for the partition function. Okay? And I did say in problem 4, you're going to have a triple integral in the numerator and a triple integral in the denominator. And I said, you don't have to do any more than that for problem 4. You don't even have to simplify it yet in problem 4, or part 4. Because I want you to see how you would generalize this. I could give you any function of the velocity components, yes? And you could put it in there. Okay? Now, step 5 is to say, okay, but let's do some simplifying next. It says cancel like terms in the numerator and denominator, thereby simplifying this expression. Okay? In so doing, you'll reduce the expression for Vx squared average into one integral in the numerator and one integral in the denominator. Then perform those integrals by using what I gave you on the front and get the final answer for Vx squared average. So what you have to be able to do is look at this expression and see what can be canceled between the numerator and the denominator, right? Because some of the integrals will cancel. Obviously this constant c cancels, that's why it's not important. Tell me what integrals cancel between the numerator and the denominator. Because this is exactly the same as this, right? So that integral cancels that one. You don't even calculate the integral. They can't cancel each other. This one cancels this one because they're identical. But crucially, you must understand that this one does not cancel this one. Because this integrand and this integrand are not the same function. Right? So you cannot cancel anything else. So at step 5, we've reduced the expression for Vx squared average to the following integral in the numerator, Vx squared e to the minus beta m Vx squared over 2 dVx, and then the following integral in the denominator, just the Boltzmann factor. E to the minus beta m Vx squared over 2 dVx. And now I say, now do those integrals, because you've simplified that as down as far as it can go. To have worried about getting these integrals here would have been a waste of your time, because they cancel anyways between numerator and denominator. You can't cancel this anymore. Now you have to do those integrals. Well, I gave you the integrals on the front. Just make sure to use the appropriate ones. This one's a plain old Gaussian. That's the first one I gave you. Integral over the entire axis of e to the minus a. Here it says x squared, right? The notation is immaterial. E to the minus a x squared dx from negative infinity to infinity is the square root of pi over a being the constant. Here, a is beta m over 2. So, for the denominator, still doing part 5, we will have square root of pi over a. Square root of pi, again, a is pi over a, beta m over 2. So there's the denominator. Then the numerator is in the family of Gaussian integrals. It's e to the minus a x squared dx times x squared. And that's the third one I gave you. That's 1/2 square root of pi over a cubed, where a is beta m over 2. So that gives me here a 2 cubed over beta cubed m cubed. Now you simplify this. Okay? You can simplify that. You get, when we simplify that, 1 over the square root of beta squared m squared, which is 1 over beta m, which is kbt over m. That's what you get. So that's Vx squared. Okay? Okay, now that we've learned how you do this, the rest of the problems just kind of fall like dominoes. Problem 6. Okay, now I want you to find for me the thermal average value of just Vx, not Vx squared. Write down the expression with integrals and then tell me what you get. So now you would just go back from here, right? And if I'm just averaging Vx, not Vx squared, you see there's only one thing that'd be different. That part. It'd be a Vx instead of a Vx squared. So here, the only thing different is that this one now be Vx, not Vx squared. So my what I've learned from that process is I can go right quickly to the expression for Vx average. There's the denominator. And the numerator and what do I get for that? I get 0. Okay? Do you see why I get 0? Why do I get 0? Which I got 2 intervals. The numerator. Right? I am integrating a function that is an odd function of Vx. Because that's odd and that's even. And an odd times an even is an odd. Okay? So I have an odd function of Vx with limits that are symmetric about 0. So I'm going to have just as much negative area as positive area. And so that is immediately recognized to equal 0. But then I say, well, I would have guessed that on physics grounds. Because Vx, roughly at any given time, I'm going to have just as many atoms going in the plus x direction as in the negative x direction. Yes? Because Vx, that's sign sensitive. Sometimes it's positive, sometimes it's negative. And I have lots of these. So when I thermal average, I expect I'm basically going to get 0. Well, it comes out of the formalism too. Okay, 7. Using similar reasoning, what is the average of the speed squared? The speed squared. Hint, you can use symmetry. I didn't even require you to write down any integrals. You could just use symmetry and an answer we've already found. So the way you do it is you say, okay, I know how now to calculate the average of any combination of velocity components. Absolutely any combination of velocity components. This is a combination of velocity components. V squared, speed squared, because I learned in physics 110 that the speed squared is the components of the velocity squared and added. So I have to take the average of that. Vx squared plus Vy squared plus Vz squared. Physics 110. Now I know that the average of a sum of terms is the sum of the average of the terms. So this is Vx squared average plus Vy squared average plus Vz squared average. Well, I've already found, have I not, Vx squared average. That was step 5. Well, now the symmetry argument comes in, because the assumption is that in this box where this gas is, there is absolutely nothing special about the x direction compared to the y or z directions. And so if I get an average for Vx squared of kBt over m, I'm going to get the same average for Vy squared and the same average for Vc squared. And in fact, it's not hard at all to see how that's going to happen. Yes? If I asked you to find the average of Vy squared, like I talked about a moment ago, you told me this would just be a 1. There would still just be a 1 here, but then there'd be a Vy squared here. Yes? Then how would this look different? Well, that would be a Vy squared, a Vy squared, a dVy, a Vy squared, and a dVy. Yes? But you see, you're still going to get kBt over m. So you're going to get that for Vy squared and Vz squared. They're all going to be equal. So V squared average is 3 times Vx squared average. Those 3 are equal. And I already know Vx squared average. So the answer for the speed squared average is 3 kBt over m. We did that, in fact, in chapter 1, using the equal partition there. Now we've done it using the formalism of the canonical approach. And then the last one, what is the average value of V squared, the speed squared, times the x component of the velocity? So what is the speed squared times Vx average value? By the way, although it is true that the average of a sum is the sum of the averages, the average of a product is not necessarily the product of the averages. So you don't want to say that. But all you do have to do is look back over here. Just look back here and think about how you would set this up. So v squared, well, it's vx squared plus vy squared plus vz squared. So you can write all that out and then multiply the vx through. And you can do it. You'll have lots of terms. Okay? But guess what you will find with all the integrals in the numerator? They're all what? They're all going to be odd. They're all going to be odd functions that are being integrated. Every single one. And when you integrate an odd function about limits that are symmetric about 0, you get 0. Right? I mean, you can just look at this. This is an odd function. Okay? You're going to get 0 for any odd function. Yeah. Okay, so I wanted to give you some practice using the canonical approach in the limit that is called the classical limit, where sums over states become integrals. Okay, so you can look at that solution some more. You're always welcome to come and ask me if you have any questions. Now, let's say pick up where we left off in chapter 6 on Thursday. I'll remind you where we left off. We were looking more, we were basically continuing to study the canonical formalism. And we said, what if we have a system that consists of more than just one object, but a whole bunch of objects, n of them. But we'll say that they don't interact with each other, non-interacting, and for one reason or another, we can tell them all apart from each other. We can put labels on them and keep track of them individually. So we have n non-interacting, distinguishable particles. How would we go about finding the partition function, right? Everything follows from that, for such an n-particle system? And the answer is that to get the partition function for the n-particle system, you merely find the partition function for each one of the n objects separately and multiply them together. So there'll be a partition function for particle 1, and there'll be a partition function for particle 2, and you just keep multiplying until you get all n of them. So this is n non-interacting, distinguishable particles. I think that's pretty much where I left off. I think I may have had one last aside where I mentioned that this kind of thinking, by the way, of breaking up the partition function into a product of separate kind of sub-partition functions is also handy, even if you had only a single particle, but you had, if you like, independent degrees of freedom. So that if you had a particle moving around in 3 dimensions, you could find the partition function corresponding to the translational motion along x. And separately from that, you could find a partition function for the translational motion along y, and another one for the translational motion along z, and then multiply those 3 together. And we're actually going to do that here in a little bit. Okay? Okay, I think that's pretty much where I left off. So now, B. I want to talk about the next case. What if we have a system of capital N non-interacting, indistinguishable particles in contact with a thermal reservoir. Okay, now they're identical particles. That's what we mean by indistinguishable. Okay? So maybe, for example, a dilute gas of nitrogen molecules, N2 molecules, where every N2 molecule is the same kind of particle. And so in quantum mechanics, we would say such particles are identical. And quantum mechanics says that you cannot distinguish between identical particles. And we're going to see that that's going to have a little bit of a consequence on how we calculate the partition function. It's going to affect the counting. Okay? All right, so the approach for finding the partition function for this system, Z, is similar to that used to derive equation 7, but we must account for the indistinguishability of the particles. Let me show you how we do that. I'll start with real simple situations so that we can see a pattern. Let's say we have a trivial gas of, say, nitrogen molecules. It consists of 2 molecules only in a box. Okay? So, first, what if we just have 2 particles? Let me show you one particular state. There's the box. Let's say at a given time, 1 particle is there, 1 particle is there. Part of specifying the state would be to tell you position. And 1 particle has a velocity that way, and another particle has a velocity that way. And I'll put a label 1 on that one and 2 on that one. That's a way, pictorially, to represent a possible state of this 2-particle system. Now all I'm going to do is change the particle labels. That's the only thing I'm going to change. I'll still have 1 particle up here moving with the same velocity as I did, and the other particle over here moving with the same velocity that it had, but now I change the labels on the particles. The method in equation 7 of just multiplying, all you would have to do in equation 7, if that was appropriate here, would be to multiply the Z1 by Z2. That's all you have, Z1 times Z2. But in that approach, it turns out that you would count these 2 states as separate individual states, and so that would count as 2. 2 states. The problem is, in quantum mechanics, you're not allowed to count these as 2 distinct states, because they are identical particles. They are not, you can't distinguish them from each other. So the wave function for this system cannot change if you change the particle labels. Okay? Which means, since the wave function is the state, that's not 2 states. That's 1 state. Okay? So equation 7 counts these as 2 distinguishable states. But for identical particles, this is not allowed. You can't count them as separate states. They're the same state. Okay? Now, any state I pick over here, where I draw the particle in a certain position and with a velocity, and the other one in a certain position with a velocity, I could make a copy by switching the labels, right? So in other words, in this two-particle system, the approach of equation 7 will exactly overcount by a factor of 2. Because for every state I put here, it's also going to count the exchange label version. But it shouldn't. So it's going to double the count. Now that's for a two-particle system. What if you have a three-particle system? So let's say you have a particle here, and a particle here, and a particle here. One's got a velocity that way, one's got a velocity that way, one's got a velocity that way, and I'll put labels on them. Now, I can start making permutations of this picture, where I draw the exact same dots in the exact same locations, with the exact same velocities, but just switch labels. Like switch the 1 and 2, or the 1 and 3, or the 2 and 3. How many ways, how many pictures could I draw? 6. There'd be 6 of them. 6 is related how to 3? It's 3 factorial. Okay? So equation 7 counts 6 states, in this case, as distinguishable. But this is not allowed in quantum mechanics. Note, 6 is 3 factorial. So I just have to remember then that if I were to just multiply the individual partition functions together, if I make one correction, I'll get the right answer for the case with distinguishable particles, because doing this will just overcount by a factor of n factorial. So I'll just do that and then divide by n factorial. Okay, so the result for Z, for n non-interacting, identical, or indistinguishable particles is 1 over n factorial times Z1 times Z2 times Zn. But we can do even more here, because they are identical particles, yes? So every one of these partition functions is a sum over the states for one of these particles, but they're all identical. So these partition functions are going to be identical. So if I have n of them multiplied together, I might as well just take one of them, say the first one, and raise it to the n power. Okay? So again, Z1 is called a single particle partition function. And the n power is because the particles are identical. All right. This will be equation 8. This, by the way, this result is also called the semi-classical limit. And we'll make that more precise a little later on, what we mean by that. But I will also motivate that chapter 7, which we're getting close to now, as we're getting towards the end of chapter 6. Chapter 7 is going to give us the tools for dealing with a situation that is fully quantum mechanical. And again, we'll make that more exact, what we mean by that, in just a little bit. Okay, so what we're going to do, well, we have a formalism now. We have a method of approach. If our system consists of n non-interacting distinguishable particles, the partition function can be found from equation 7. You have to find the partition function for each of the particles separately and then just multiply them together. My example of this situation was the atoms in an Einstein solid. They're distinguishable from each other because they're not overlapping each other. They're in their own little lattice positions as they oscillate. And they don't overlap each other, so you can tell them apart. And then we've done this situation where we have n non-interacting, indistinguishable particles. They're identical, and they're moving around such that they overlap so much that you can't tell them apart from each other. Okay? Then we're going to use that result for the partition function. Okay? Yes?
So, for example, if you have like a container with and all the particles of the gas are exactly the same, like indistinguishable. So then one wave function will be able to describe the whole thing.
Yes. There'll be an n-particle wave function. Okay? It'll end up being a product of single particle wave functions. But it will have to be properly symmetrized. As we'll learn, at least if we're going to do the fully quantum mechanical approach, we'll learn how to do that in chapter 7. But if it's a dilute system, then it's really just going to be your n-particle wave function is going to be a product of n single particle wave functions. Just like the n-particle partition function is a product of n single particle partition functions with this one subtle term for overcounting. And I will tell you that even though I think I've made that n factorial seem like it makes sense, this boggled people for a long time. This 1 over n factorial. They didn't realize it needed to be there for quite a long time in the history of statistical mechanics. They didn't realize it needed to be put there. They didn't think about it. Didn't put it in there, started getting results that didn't make physical sense. And Gibbs went back and said, well, you're not doing the counting right. And Essence led people to put that in. But that was subtle for a while, that counting. Okay? Okay, but we know we're going to use that result if we have n non-interacting, indistinguishable particles. Classical example of that is an ideal gas of identical particles, like nitrogen. Okay? Now, let me emphasize, all this is completely wrong, 7 or 8, if the particles interact with each other. At least more than weakly, i.e. W-E-A-K-S-Y. Okay? If they interact with each other, you know what you got to do? You got to go back to the definition of Z, and you've got to take the Boltzmann factor for the total energy of the n-particle system, and you've got to sum over n particle states. And the n-particle wave function will not now be a product of n single particle wave functions because the particles interacting with each other. You have to go back and solve Schrödinger's equation that includes all n particles altogether, which is practically impossible. Then you got to come up with alternative approaches. How do you deal with it? Then you learn about things like perturbation theory and other techniques. Okay? That's what you learn in graduate school. All right? They'll do the stuff that we're doing here in about a week and a half. We've been doing it for, what, 13 weeks now? Okay, they'll do what we've been doing in about a week and a half, and then they'll start worrying about systems where the particles interact. Okay?
So at that point, they're just approximations. Okay.
Or numerical work, where you use numerical techniques to calculate this numerically. And there are very fancy ways to do that. Quantum Monte Carlo methods, you might learn about someday. Okay, but what we're going to do, we're going to take our break, and when we come back, we're going to close out Chapter 6 by hopefully, if you haven't yet, convincing you of the beauty of this approach by applying it one more time to the ideal gas, but not the monatomic one. We've done that. We've nailed that. It's done. We'll do a diatomic ideal gas, where the molecules have more degrees of freedom. And how do you deal with the other degrees of freedom that are in addition to translation? We know how to deal with that if we have the equipartition theorem. But what if the equipartition theorem isn't valid because the temperature is too low? This is a formal approach that will enable us to find the partition function for a gas of diatomic molecules that we will be able to then solve for the average internal energy, the heat capacity at constant volume, whatever. And it will in essence be exact. So that's what we will do. We'll take our break, then we'll come back. Okay, we'll look at my folder.